All right, so today we're going to review linear algebra just really quickly, not extensively, not comprehensively. Everyone here knows linear algebra, right? Okay, so we'll be super fast about it. Yeah, for this class, you don't need to know the thorough details of linear algebra. And then we'll start talking about support vector machines, which will be the last non-neural network supervised learning algorithm that we talk about in this class, because there's a lot of other aspects to machine learning besides supervised learning, and we will get to that. But after SVMs, you will know all the mainstream, besides neural networks, machine learning models, which will be super exciting. So whenever you use them in sklearn, you'll know how they work under the hood. So quick review of linear algebra. Linear algebra is all about doing operations, and specifically algebraic operations, with matrices. And a matrix is simply a grid of numbers. So for example, this is a matrix that has dimensions 2 by 3 rows and 3 columns. Why do we care about matrices in computer science and in machine learning? Well, matrices can represent many things. Matrices can represent many things. And often when you first learn about them, they represent a system of linear equations, but they actually can represent many other things, and we can make them do a lot of things beyond systems of equations. So for example, and we talked about this a little on the first day of class, they could represent images. And so when we talk about computer vision in this class, which we'll talk a lot about, we'll get there, that's represented as a matrix. Tabular data, which we've been mostly working with so far in this class. So tabular meaning a table of a table, tabular, is represented as a matrix, where each column represents the column that you might see in a spreadsheet, and each row represents each row that you might see in a spreadsheet. And where each row would be a different data point 1, data point 2, etc. I'm just putting random numbers here. This is unitless. And many other things. So we care about matrices for those reasons. There's a couple of operations that we can do to matrices. So one of those is transposing a matrix, and that's denoted like so. So this represents the transpose of matrix A. And what that does is best seen through an example. So we're calling this matrix A the 1, 2, 3, 4, 5, 6. So if we transpose it, basically rotate it, then we get this matrix. So the rows become columns, the columns become rows. So that's one operation. Another operation is taking the inverse of a matrix. So that's the inverse of matrix A. And there's a way to calculate it specifically, but it doesn't really matter for this class. All that we need to know is that a matrix times its inverse is equal to something called the identity matrix, which is like 1 in matrix form. So the identity matrix is where we have zeros everywhere except ones in the diagonal. So for example, this is a 3 by 3 identity matrix. And a matrix times the identity matrix is equal to itself. So that's why it's called the identity matrix. It's like multiplying by 1, but in many dimensions. So a specific type of matrix is a vector. So vectors are n by 1 matrices, and that's a vector, that's a vector, etc. These are all vectors. And conceptually, they represent a point in space. Represents a point in space. So for example, the vector 3, -2 would represent, if we drew a coordinate system with 3 on the x-axis and -2 on the y-axis, but we'll label it x1 and x2 because it's the first dimension of x and the second dimension of x. And if you're a computer scientist, it would be x0, x1. But if you're a mathematician, it would be x1, x2. Sorry, random fact. So represents a point in space. So there's certain operations that we like to do on vectors. So we have the norm of a vector. The norm of a vector represents the magnitude, kind of like the length, the magnitude of a vector. And the equation in 2 dimensions, so what we call the L2 norm, or the norm in also 2 dimensions, is the square root of each of the components of the vector, and the reason why is simply the Pythagorean theorem. So if we draw x1, x2, and we get x1 is there and x2 is there, and this is our vector, then this would be, so this is the vector x, this is the norm of x, this is x1, this is x2, so using a squared plus b squared equals c squared. That's the magnitude of a vector. This will come up later. We have dot products, which is, there's many types of products in linear algebra, and we don't care about all of them in machine learning. So you might have heard of the cross product. Not so interesting in machine learning, but the dot product is. So the dot product, if you take the dot product between 2 vectors, so let's say we have that vector and we dot it with that vector. We're going to see the dot product again and again, by the way. It is the first elements multiplied plus the second elements of each vector multiplied plus the third element of each vector multiplied, which in this case just happens to be -1. And the dot product has somewhat of a geometric meaning as well. So there's a formula A dot B is equal to the magnitude of A times the magnitude of B times the cosine of theta. When we did NLP, did we talk about cosine similarity? No. We didn't? Okay. So we'll talk more about that when we talk more about NLP. I could have sworn there was something about cosine similarity in that coding notebook, but we will get to it. So basically, this theta represents the angle between two vectors. And so if you have what are called orthogonal vectors, and the notion of orthogonality is useful in many things, but probably not too important for this class, then the dot product is 0, because the cosine of 90 degrees is 0. Cool stuff. Okay, so then we also have matrix multiplication, which is definitely not needed in this class, but if you're curious, you have a matrix like so. I'm just giving indices to different elements of the matrix, and we multiply it by this type of matrix, B, with the corresponding indices. So indices are row, column. Then the way we find the multiplication of the two matrices, the product, is that we select the row that we're multiplying by. So let's say to get this top position, we would look at where the top row of matrix A intersects with the first column of matrix B, and that represents the first element of the product matrix. So we take the dot product between the rows of matrix A and the columns of matrix B. So for example, this first element would be A11 times B11 plus A12 times B21, just the dot product. And we do something similar. Let's just look at one more example. So if we wanted this position, which would be the bottom right position, because it's where the row of matrix A intersects with the column of matrix B. That would be A31 times B13 plus A32 times B23, and etc. for the other parts of the matrix. Never going to ask you to multiply matrices in this class, but if you ever, on the course website, there's more mathematical proofs of all the algorithms that we learn about. And while you don't need it for this class, if you ever want to interview to be a data scientist, they probably still won't make you know that. But if you want to be, a researcher, then it's good to know this stuff, and to make a lot of the derivations make sense, it's good to understand why when you multiply two of the matrices, you get a certain result. So it's from that. So more specifically, or just to write it out, the dot products between rows of A and columns of B. Okay, so no more linear algebra. Just wanted to get us all on the same page. Sorry to make the first 15 minutes of this class super boring. One interesting notation, though. So a lot of times, I know I said we want to talk about linear regression and logistic regression ever again, but until deep learning. But if you wanted to write linear regression, and it's commonly written this way, as a linear algebra equation, and a lot of the mathematical machine learning resources, write it this way. Well, we know our equation for linear regression is as follows. Oop, forgot the W. W n x n plus b. So we could write that as simply a weight vector times the input x vector plus b. And so a lot of times a compact way of writing linear regression, and instead of putting all the dots, you just write it as two vectors, the dot product between them, which happens to be the first vector transpose times the second vector using the matrix multiplication rules. So I'm a little mixed. That's basically all the background you need for the next few lectures with respect to linear algebra. It turns out that using linear algebra, we can derive a very exact, and so very is not needed, just an exact equation for the solution of linear regression, or that is an equation for the parameters that minimize the mean square error without doing gradient descent. That is, we just run the equation and we get the exact solution. That only works for linear regression. If you get more complex models, it no longer works. So it's kind of a special case because linear regression is such a simple equation. We're not doing Wn times xn squared or times the square root of x. It's just a linear equation. There's an exact solution. Do y'all want to see that derivation or no? Who wants to see it? Who doesn't want to see it? Oh man, it's kind of tied. We got low participation. Okay, let me do just a really quick. It's kind of cool, although no one even uses this in the real world for linear regression because it has big matrix multiplications in the solution, and if you have a really big data set and you're multiplying huge matrices, that's computationally inefficient. And might as well just do gradient descent. So even in the real world, people don't really do this. So maybe I'll just do a really condensed version to make everyone happy. That's general goal of this class, make everyone happy. So for a data set, and this is kind of nice review for a linear regression for the exam anyway. So for a data set, let me time myself so I don't get carried away on this, because it is super cool, but I know y'all don't like. Okay, I put a 5-minute timer, so this will go off if we're still. So, okay, so for a data set with 3 points, for example, we could write it in a linear algebra way as y1, y2, y3 is going to be estimated by the following matrix values times our parameter values, which we can write concisely as the X matrix times the theta matrix. And if you do the matrix multiplication of setting it up this way, you find out that this X theta matrix is simply theta 0 plus theta 1 x1, so should look familiar. Theta 0 plus theta 1 x2, and theta 0 plus theta 1 x3. Here the subscripts of x are the data point index, not the feature index. And so what we want to do is minimize the mean square error. So we can write that in linear algebra, as a linear algebra, expression. So minimize the norm, or the distance between the true value y and our predicted values x theta, which is simply the normal theta 0 plus theta 1 x1 when we expand it out. And so, we could write it as, actually I'm just going to write it like this. So y minus x theta times y minus x theta, so the mean square error. And there's a bunch of linear algebra, but we're just gonna do dot, dot, dot. And that eventually comes out to be this ugly looking equation. So definitely don't memorize this. 2 theta transpose x transpose y, not done. Machine learning classes where they teach you linear regression like this, which, hopefully the way we learned it was more educational. To find the minimum of this expression, we can do what we always do, take the partial derivative with respect to the parameter values and set it to 0. So the partial derivative of that above, using calculus for linear algebra, turns out to be this also ugly expression, plus 2 x theta x. We set that to 0. And then if we solve for theta using a bunch of linear algebra, we get theta equals x transpose x, inverse of that, times x transpose times y. So that's the exact solution for linear regression. And it's often called the normal equation. And it is an analytical solution to linear regression. And again, only works for linear regression. For more complex models, you can't do this, but if you ever see that equation floating around, that will give you the exact parameter values which minimize the mean square error. So now you know that, and 13 seconds to go. So that worked out well. Okay, any questions on linear algebra as we covered it here? Okay, let's go to some fun stuff. So now we're going to talk about, new section, the final supervised learning method that we're going to learn about besides neural networks. And they are called support vector machines. And this is a fun topic, in my opinion. Who used a support vector machine for homework 2? Okay, a couple people, good. Cool, so let's learn about how that works. It's often one of the best performing models, and a little bit of history about support vector machines. They were invented in the 90s, so they're not that old. And up until, I don't know if it's the late 2000s or early 2010s, they were the best method. They were the neural networks of that time period. If you wanted to get a model that was going to work really well for big data, support vector machines is what you used. Of course, now it's neural networks, but that's only been for the past 15 or so years, which, grand scheme of things, is not too long. So a lot of times in the literature, you'll see people using support vector machines because they were kind of the best method for a while. And the basic idea of support vector machines is relatively simple. The basic idea is to explicitly find the maximally separating hyperplane. So in one dimension, where we just have x1, that would be, we had some points here in one class and some points here on another class. We would be learning the maximally separating point. So maximally separating point. And we're gonna think in higher dimensions today, which will be a little bit fun. Let's just build the intuition. And I think we've hinted at this type of intuition before, but let's just draw it out. So if you have two dimensions that are separated like this, then, and I know you've seen this a lot in this class, we're learning the maximally separated line. Maximally separating line. In 3 dimensions, so x1, x2, x3. Okay, let's see. So I'm going to draw some red points up here. And so, oh, sorry, those are blue points, and some red points down here. And maybe the plane could kind of look like that. And plane that separates the data points, and this is what we drew is the plane that maximally separated the two categories. This is my best attempt to draw something like that. So these dotted lines are the distance between the points and the separating shape. So let me draw that in the lower dimensions too to be a little consistent. I won't draw that in one dimension because that would look really ugly. And when the input dimensionality is greater than 3, which it usually is, and usually we can't visualize our data like this without dimensionality reduction, which we'll learn about later. When the input dimensionality so just to be thorough, that's the number of input features. I think you all already know that. Is greater than 3. Then what we learn is the same concept, a linear shape, but a linear shape in many dimensions. And the generalization of a plane is a hyperplane. So a hyperplane is a plane in many dimensions. So a maximally separating hyperplane, which, if we have 4-dimensional data, that might look like a plane moving through time. And if we have, 5-dimensional data, then it might look like a thing moving through time. Sorry, this is getting kind of abstract. So we'll stop it there. But I think you get the idea. Linear separating boundary in a high number of dimensions. Any questions on that? This notion of high dimensionality and a linear boundary in high dimensions. Is it intuitive? Okay, cool. So for the rest of this class, all our examples will be in 2D because that's easy to draw, but it's the same concept. You just add another x subscript, whatever, to make the same concept work in higher dimensions. So in 2 dimensions, we want to find specifically the maximally separating hyperplane. So we might have this hyperplane, which separates data, but not maximally. And if we were learning logistic regression, it might just end up there and stop, but it's not, and it would have low loss, defined by cross entropy loss, but it would not necessarily maximally separate the data points. And where it ends up in logistic regression kind of depends on how you randomly initialize the parameters. Good thing to think about. You could have a plane that just doesn't separate the data, so that's not good. Doesn't separate the data. But what we want is neither of these. We want a plane like this, which separates the data maximally.
What do you mean by maximally separating something?
So basically it means that the distance between the circles is just as much as the distance between the distance between the circles in the plane is just as much as the distance between the x's in the plane. So it's basically in the middle.
So if you had way more data points for one of the variables, would the line be closer to that one? Is it all the distance added up?
Yeah, well, we're about to get to that, but basically, no, it depends on the boundary, the ones that are closest to the plane. And those are what are called support vectors. So we'll talk about that now. So there's 2 general types of support vector classifiers. We're going to start with the hard margin SVC, which is, I think, what your homework asks about. So when we say SVC, that's support vector classifier, which is a building block to support vector machines. And the idea of a hard margin support vector classifier is to find a margin which doesn't allow for violations of the margin, which doesn't allow for violations of the margin. So hard margin SVC requires your data to be linearly separable, which is a big assumption. We'll get to how we break that in a bit. And so let's start putting all this to math, but not too much. So x1, x2, gonna draw some points in one category and some points in another category. And what we want to do is find the boundary that most separates them. So we're going to draw that here. And So in support vector classifiers, one kind of standard that kind of gets a little confusing is that instead of labeling in binary classification the labels as ones and zeros, we label them as +1 and -1. And the reason is really just for mathematical convenience. It makes some of the equations later on more convenient. In principle, you could have made them ones and zeros, but the math works out better if it's ones and -1s for support vector classifiers. And it's not like this is something of nature. These are things that people engineered and made up, so that happen to work well. So you can, when you're creating your own machine learning models, you can make them however you want. Make it convenient for you.
So is the -1 here equal to 0, or does that matter?
It doesn't matter. It's just one is one and one's the other. And so we're going to say that for this line, or if it's in higher dimensions, hyperplane. So now we just use linear algebra notation, all that linear algebra background basically for that. We're going to set the boundary to be, the separating boundary to be 0. And we want to then have margins at important points which are closest to the separating line, which are called our support vectors. So that point and that point are all our support vectors because they're what support the decision of the separating boundary. I assume that's why they named it that. And so the line that goes to each of our support vectors is going to be assigned to +1 for the positive class. And let's just make it linear algebra notation now that we know it. And -1 for the negative class. It might be much less than -1 as we go lower below that line and much above +1 as we go above that line. Now, an important thing to notice here is that the y is coming off the page. So we're not drawing the y-axis here. So it's not like this is the equation for the line in 2 dimensions. We're saying that's the equation for the plane or hyperplane, and we're setting it equal to a y value, which is coming out of the page. That's the value that's of the class label. So we want to find a equation for the margin. So this would be the margin. And the way we can find it is relatively simple. We can take our 2 equations above, so W transpose X plus B equals +1, and W transpose X plus B equals -1. And we could subtract them, and basically using linear algebra, because you can't subtract can't necessarily subtract matrices. But using some linear algebra tricks where basically we divide both sides by the norm, we can get that our margin is equal to 2 over the norm of W. And so that's a specific equation formula for the margin. And so what we want to do is to optimize that margin. So the math goal is to maximize that margin. We want to maximize the distance between the separating margin equations for each class. So maximize the margin, which, as we saw, is 2 over norm of W, subject to certain constraints. And this is a slightly different type of optimization. So one constraint is that the margin has to be greater than or equal to 0. We can't have a negative margin, doesn't quite make sense. How would you even have a negative margin? And we want our equation for our separating boundary to be greater than or equal to +1 if the corresponding y value is +1. And similarly, we want it to be less than or equal to -1 if yi is equal to -1. So it's just kind of from this picture relatively intuitive. We're just putting it into an equation now. We're saying the margin has to be greater than 0, that our weights and bias have to be such that the value is greater than +1 if the true value is +1, and less than or equal to -1 if the true value is -1. And oftentimes you'll see this stated more concisely. So these two constraints are just saying classify everything correctly. So a more concise way of writing these two equations that you'll often see people write it as is yi times W transpose xi plus b is greater than or equal to, 1, greater than or equal to 1, which is the same thing, because if you think about what happens when the true value is 1 and the actual value is 1 versus when the true value is -1 and the actual value is -1. In both cases, when you multiply it out, the result is greater than or equal to -1. To +1. So that is exactly what we want to do. So we can restate this as a minimization problem, which is useful if we want to, I don't know. Usually we think about minimizing things when we're optimizing for machine learning. So just minimize the reciprocal and remove the fraction, which, as we talked about, a constant, maximizing or minimizing a constant times something is the same as maximizing or minimizing the original thing, subject to yi, basically the constraint that we wrote above, plus b is greater than or equal to 1. So that's really the goal of a hard margin SVM. And we can solve that using optimization methods that are similar to gradient descent. We can't exactly use gradient descent out of the box because we have constraints in here. I think the math is really cool for how to solve constrained optimization problems. It might be a little bit much, so let me just point you to it. So if you want to learn about how to solve constrained optimization problems like this, or maybe you already know about this, then check out Lagrange multipliers. Who's already knows about Lagrange multipliers from? Okay, so yeah, so for those who know, just use this and then solve it as a regular optimization problem. For those who don't know, don't worry about it. But if you want to learn, check out Lagrange multipliers. It's commonly taught in like multivariable calculus, so kind of higher level calculus classes. Okay, so that's hard margin SVM. And if y'all really want to learn about Lagrange multipliers, we can do that in the future. But there's so many other cool machine learning things to talk about. But Lagrange multipliers are also cool. Any questions on hard margin SVM? Okay. So let's go to the next case, which is what if the data are not perfectly separable, which is a reasonable question. We often have data sets where you can't just separate everything with a line or a plane or a hyperplane. So we can make a tiny modification to hard margin SVMs to get what's called a soft margin SVM. Oh, by the way, now you know everything you need for homework 3, because that just asks about hard margin SVMs. But good to know about this stuff too. So a soft margin SVC allows for misclassifications but penalizes them. So for example, we have our data drawn in 2 axes, and it's going to be mostly linearly separable, but it might be somewhat and really barely not linearly separable. So the data is mostly linearly separable, but not perfectly so. So what we do in a soft margin SVC, I'm going to draw the screen a little bit behind here just to make this picture a little nicer. So we still want to find maximally separating boundary, just like with hard margin. But we also want to penalize misclassifications. So that is misclassified by that much. This green point is misclassified by that much. And we call these misclassifications, it's often using that Greek symbol for some reason. I think because it kind of looks like E for error. So what we do mathematically is exactly what we see above, introduce a slack, we'll call it a slack variable. And so our new objective function is to minimize the norm of W, just like before, just like for hard margin. But we add a term which hopefully concepts start to connect in a second, times the sum of all of our errors, basically, our slack variables, and where the C constant is, anyone tell me what this is going to be? It's a hyperparameter. It's another hyperparameter, which should look similar to regularization. There's a constant that a user sets, a hyperparameter, times the sum of the things that we want to penalize. So again, we're trying to minimize something, but we're adding terms because we're penalizing having things we don't like. So in L1, L2 regularization, the things we don't like are having too many model weights. In this case, the things we don't like are having things on the wrong side of the margin. Either way, we penalize it by adding it to the loss function that we're trying to minimize. Make sense? Hopefully concepts are connecting. Whenever you see a loss function and it has a plus constant times sum of things, probably a regularization term or a penalization of things that you don't like. So sorry, we're minimizing that subject to, still have the constraints. So really the same constraint as before. So the true value times the predicted value is greater than or equal to 1, but you can subtract out the error from it. And we require the error to be greater than 0. So you're not doing this if it's doing really well, only if it's doing badly. And we could actually use a loss function for soft margin SVMs. It's a relatively popular loss function. Sorry, question?
Just wondering, like, we have something like a soft margin.
Hmm?
Why not just always use it anyway? Because it kind of covers the hard margin case. In real world data is more like this, isn't it? It's not that easy to separate.
Yeah, so the question is, if we have a soft margin SVC anyways, why do we even have hard margins? 2 answers. One is that really hard margin's a building block to soft margin, so it makes it a little easier to explain. But the second reason is that if you know that your data is definitely linearly separable, it's a little bit easier to do the math for hard margin SVM. Even though a computer is doing the math anyway, so it's not that hard for a computer to do the math. Okay. So with a soft margin classifier, we can use a loss function called the hinge loss function. This is a relatively popular loss function outside of SVMs as well, I think. And so the hinge loss is equal to the max of 0 and 1 minus the true value times the predicted value, which let's break down this loss function. So the properties of the hinge loss are that if we make the correct prediction, so if y hat is correct, but the absolute value of y is, of y hat is greater than or equal to 1, which means we're really in our margin. We're either way above +1 or way below -1. Then the hinge loss is 0 because because if it's greater than 1, 1 minus the multiplication of y and y hat is going to be super negative, and so the hinge loss just becomes 0 because we're taking the max of 0 and that really negative number. So if we're doing really well, hinge loss is 0. And remember, we want to minimize loss. If y hat is correct, but the absolute value of y hat is less than 1, so that means we're technically on the right side of the, when I say right, I mean correct side of the margin, but we're not, we're kind of before we get to the support vectors. So in between the margin and the support vector, so not so great, not super confident. Then the hinge loss is between 0 and 1. And if we look at the equation here, that would be, we're taking 1 minus this multiplication term, which is only positive if both signs are the same. So if the predicted thing's negative and the actual thing's negative, but if they're relatively, and y is always 1 or negative 1. So if the y hat prediction is a fraction less than 1, between negative 1 and 1, it's not, the classifier is not super confident, and this equation gives us something between 0 and 1. And then finally, if we make the wrong prediction, so we're on the wrong side of the boundary, so if y hat is incorrect, then the hinge loss is greater than or equal to 1. And remember that we're trying to minimize loss, so the hinge loss is high, and that's not good. We want to minimize that loss. So we can just draw hinge loss as a picture just to see what it looks like. It's a common loss function, and you'll often see this picture.
Is there a scenario where hinge loss could be equal to 1?
So there's a,
As in, not like, I guess I was just confused by the first one. Like, why is it equal to 0 and not, or I guess, sorry, second one, why is it greater than 0 and why not greater than equal to 0?
because if it's 0, that means that we're correct, and y hat is greater than or equal to 1. So it's going to be equal to 0 in the first. The equal to 0 is covered in the first scenario.
What is y hat?
The
Is it
predicted.
Like a hyperparameter, or?
Y hat's predicted value, just
Oh,
like
it's the
in
same
homework
notation
1.
from before.
Yeah, same as
Oh.
in homework 1. Y hat's the predicted value, y is the true value. Yeah, maybe let's write that out. So recall that y hat is the predicted value, and y is the actual value. Okay, so if we are here, then we are on the correct side of the boundary, but inside the margin, which is okay but not great. If we're out here, we're in the correct side of the boundary, and outside the margin, which is great. Great scenario to be in. And if we're out here, we're in a really bad situation because we're in the incorrect side of the boundary. Let me just give this a label. We should never draw plots without labels. So the x-axis here is going to be the multiplication of yi with y hat sub I. Any questions? Okay. So now you understand support vector classifiers, which are not quite support vector machines because we're missing one ingredient. And to build up to this ingredient, let's ask another question, which is, before we asked, okay, what happens when, what if the data are not perfectly separable? That means that they're mostly separable, but not perfectly separable. So soft margin's good in that scenario, but let's make this a new category. So what if the data are not close to being separable? So what if the data are not even close to being separable? Okay, and the answer to that is kernels. And so a support vector machine is a support vector classifier plus kernels. So what's a kernel? The basic idea of a kernel at a high level is that, let's say we have data that are super duper not separable. So for example, if we have some blue points out here and some blue points out here and some red points in the middle, and we're just working with a one-dimensional input, just y equals mx plus b. Drawing that out, there's no point that's going to separate the points well. So what a kernel allows us to do is to project our data into many dimensions. So remember how we talked about dimensionality reduction, and we're going to learn all about that later? This is kind of the opposite of that. We're doing dimensionality. What's the opposite of reduction? Addition, not quite addition. Increasing of the dimensionality, I guess. And what happens when we do that is that we now, so let's say we have our original x-axis and a new axis, which is our x-axis squared. So what happens is that if we project our data into this two-dimensional space, which I'm going to draw really loosely. Yeah, so now it's a quadratic function. Now in this two-dimensional space, there is a linear, if I draw it right, a linear, maybe not in the way I drew it, but you could see how this would work. A linear separating boundary. So linearly separating boundary. I'm kind of tempted to redraw this so it really is a straight line, but y'all get the idea without me drawing. Okay. So that's the cool thing about kernels is that if you have low dimensional data that are not linearly separable, if you project it out into a high dimensional space, it will be linearly separable if you have enough dimensions and the right dimensions. But it's kind of hard to do. And isn't that cool? Like, you can take any crazily separable, like not separable data and just put into high dimensional space, and now you can use lines or high dimensional versions of lines to separate them in that high dimensional space. So that's the basic idea of kernels. So map data to high dimensional space. And just what I said before, the key idea is that non-linearly separable data, non-linearly separable data are, I'm not going to say are, I'm going to say can be separable in high dimensions. But if you get the dimensions right, it can definitely, and you have enough dimensions, it could definitely be separable. The issue with doing this, though, is that separating our data in high dimensions requires operating on really, 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 really large dimensional data. So like, if in order to make, let's say we have a data set with 10,000 features, so 10,000 dimensions, pretty reasonable sized data set. That's actually kind of small, medium in the real world, 10,000 axes. That's tiny. Like Facebook uses much larger data sets, many more features than that. And so if we want to separate that, if we want to project 10,000 dimensional data into a high dimensional space, now we're talking in the billions of dimensions or even trillions of dimensions, or technically including even infinite dimensions, and there's a way to do this with infinite dimensions as well. You can't represent that well on a computer. It's going to be very memory inefficient. Even if you had enough memory, it would be computationally inefficient to work with that. So how do we deal with that? Something to think about. Yes?
Why would we want to do billion dimensions? Like at the end of the day, we should be able to visualize this whole mapping thing, right? And it's kind of difficult to visualize beyond like 5 or 6.
So if it's so the question was, why do we need to go to a billion dimensions? The reason is that if you have, so you're starting with 10,000 dimensions, and you want to be able to separate your data linearly. So it might require billions of dimensions to separate it linearly if you're starting with 10,000 dimensions. Because I don't know what a billion divided by 10,000 is, but it's plausible that you would need that many dimensions to.
10 raised to 4. Oh, 10 raised to 5.
Yeah, so it's feasible that you need that many dimensions per original dimension in the high dimensional space. Do that to all your dimensions. It's not infeasible that you have a highly inseparable data set and you need many, many more dimensions to separate it. Yeah, I drew a simple example here, but the real world, it might be blue, red, blue, red, blue, blue, red, 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 etc. And that's just in one dimension. It can get complicated. In 10,000 dimensions, it can get really complicated. There might be tan to the -1 everywhere, and a 30,000 page equation that describes the separating boundary, which is pretty complex, but also pretty real world. That's often what we get. So we need to be able to deal with these highly complex data sets. First, let me write down this problem just so it's written on the notes. So the fundamental issue is that moving a reasonably sized data set. Sorry. Feature space. And, feature space, feature dimensionality, input dimensionality, all mean the same thing. So, for example, 10,000 features, as we discussed, into a huge feature space, which may be required to separate the data, may be required to linearly separate the data, e.g. 10 to the 10 features, just kind of chose that arbitrarily, is computationally infeasible. Computers don't have enough memory or processing power to deal with that. So while mathematically it can be good to do that and you could find a separating boundary, computers can't do it. So the solution to this issue is called the kernel trick. And some quick math background, which is I have 2 minutes. So outside of the scope of this class, so outside, not the kernel trick, but this outside this parenthetical statement that's kind of important, outside the scope of this class, an equivalent formulation of SVM is, which it's outside of the scope of this class because you can derive it again with Lagrange multipliers, and it's kind of this long, tedious mathematical proof. And the exact equation here, again, doesn't matter, just a small part of it matters. If you know about Lagrange multipliers, these alphas are the Lagrange multipliers, but again, not a big deal to really understand that. Just know that we can do some algebra and rewrite the objective function above as the following. So this is an equivalent way, just using a bunch of algebra. We can rewrite what we derived earlier as this. And the key observation, which I guess we'll continue on next class, is that everything here, all these terms are scalars, so they're not computationally challenging. And the computational challenging part are these X matrices or vectors that represent our data. That's the computationally expensive part. So as we scale up in dimensions, we have, we're taking these really big dot products, which is, X transpose X of two different data points in the high dimensional space. And so what the kernel trick allows us to do, and we'll see this next time, is calculate a dot, know the answer to the dot product in high dimensional space without taking the data to the high dimensional space. So you can say, what's the dot product of this vector with 5 elements with this other vector in 5 elements if you had projected those two 5-dimensional vectors into 10 billion dimensional space? And the dot product's just a scalar, it's just a number. So you get the result of that dot product without actually doing the dot product. So we'll see how to do that next class, but we're out of time. Should be fun.